Hello students. Class 11th physics, and we have this topic, units and dimensions. It is the second chapter and first topic of this second chapter. So uh, before we start, let's talk about physical quantities. In physics, in order to predict something, in order to formulate something, in order to uh, calculate something, we require some kind of parameters, some kind of terms, and we call that term as physical quantity. So a physical quantity is a quantitative, a measurable thing by which we can measure, we can correlate it with certain other things, and in order to explain the physical phenomena or any other events that are taking place around us. So now a physical quantity can be classified into different forms, different ways, but here I'm dividing physical quantity, I'm categorizing it into two parts: fundamental quantities and derived quantities. So this time I'm classifying them on the basis of whether they are depending on other quantities or not. So if physical quantities are independent of any other quantity, then we call them fundamental quantities. And if they are derived from any other quantity, then we call them as derived quantities. So I haven't mentioned anything here, but let's start from this fundamental quantities. So fundamental quantities, as I told you, are fundamental, which are independent of any other physical quantities. So these are length. Length means uh, anything which we are measuring uh, as a span, as a gap between 2 points. So length includes length, breadth, height, depth, radius, diameter, circumference, perimeter, wavelength, and whatever you can imagine, the distance, displacement. So whatever is there which we are going to measure using a measuring tape, which we are going to measure to calculate a span between 2 points, will be considered as length. Then mass, all of us know about mass. It is the quantitative measure of inertia of a body. Time, the span between two events: temperature, degree of hotness, coldness; electric current, rate of flow of charge; luminous intensity, the brightness; and amount of substance, that is mole, how many mole are uh, there in a specimen. All right, so we'll start with this length. So we know that unit of length is in terms of meter. SI unit is meter. I am considering SI unit here. So it is meter, and its dimension is L. So uh, so in terms of length, we are going to measure it in SI unit. It is meter. In CGS unit, it will be centimeter, and sometime for higher measuring unit, we use kilometer, and for astronomical length, we use light year and astronomical unit also. But we'll stick with this SI unit, and that's why I'm here meter only. Similarly, for mass, SI unit is kg and its dimension is m. Then time, SI unit is second and dimension is capital T. Then temperature, SI unit is Kelvin and dimension is also represented by K. Electric current, SI unit ampere and dimension is A. So after length, mass and time, rest of the physical quantities, uh, whatever be their SI unit, the same is the representation of their dimension. Luminous intensity, candela, dimension CD, and amount of substance, mole. So now if we talk about derived quantities, so the quantities which are made up of some other quantities, especially that is fundamental quantities. So like area of a square. So we know the formula is side multiplied by side. So uh, its SI unit will be meter square, because one side will be measured in the unit meter and other also in meter, so meter square, and its dimension will be L2. You can call it L square, but we generally call it L2. So area of circle, we know pi r square. Now pi is just a number, a pure number, and a pure number is dimensionless. So only r, that is radius, which is length again, so its SI unit is meter square and its dimension will be L2. So from here we can conclude that no matter um, uh, which geometric figure we are taking, if we are measuring its areas, then its unit will be the same, meter square, and its dimension will be the same. So it means that if a physical quantity, if there are a number of physical quantities but they have same nature, then their unit and dimension will be the same. Okay, now a few more example like volume. Now we know that as here we have taken area and its unit and dimension were same. So also I'm taking volume of a cuboid, but that will be the unit and dimension will be the same for any type of volume. So volume of a cuboid, we know it is length into breadth into height. So meter into meter into meter, that is meter cube, and dimension is L3. Okay, now moving on, density. Its symbol is rho, Greek alphabet, and its formula is mass upon volume. For mass, SI unit is kg, and volume, SI unit is meter cube, as we have already obtained here. So its dimension of mass divided by dimension of volume. So dimension of mass is capital M and dimension of volume is L3. We write it like this: ML minus 3. List goes on and on and on. So quickly, some other physical quantities which are essential for upcoming few chapters. Okay. So most what I can say awaited and most used physical quantity, speed, equal to distance upon time. Distance, again, a span, a length. So, because it is length of the path, its SI unit is meter upon second. It is better to write it like this, ms minus 1. And its dimension of distance is L, dimension of time is T. So finally it is LT minus 1. Now same thing is for velocity. So velocity, we know velocity is displacement by time, and yeah, of course, these are two different things. They have different nature. Speed is different from velocity. They have a theoretical difference between them. So conceptually, both are different quantities. This is independent of direction. This depends upon direction. This scalar vector quantity, we are going to study it in the later sections. Okay, so again, its unit is dimension is also LT minus 1. And I hope you can understand this easily, because displacement is again a length and time is time. So from here we can say that these both physical quantities have same dimension, but it doesn't mean both are same. Both physical quantity can have physical quantity can have dimension, but they need not to be the same, of same nature. So they have different nature, but their unit and dimension are same. So be careful about there can be many physical quantities which can have same dimension, but they have different nature. Okay, next, there is momentum. Its symbol is P, so P equal to mv. Its P is the symbol for momentum. Mass into velocity. So mass, SI unit is kg, velocity meter per second. And its dimension, so dimension of mass is capital M, and dimension of v, velocity, is LT minus 1. So once you have just understand the concept of dimension, and you are able to find out the dimension of these basic these common formulae, then you can easily find out the dimension of complicated terms also. Now moving on, force. Okay, so force, there are two formulae, and I'm going to tell you by both the ways. F equal to ma and F equal to delta p by delta t. Change in momentum upon change in momentum. Ultimately, if we find still it is momentum. If we subtract two things, like if I subtract 5 second minus 2 second, still it is 3 second. Still the answer is in terms of second, means still it is time. So in the same way, delta p means change in momentum, still it will be momentum. So momentum mlt minus 1 divided by t. So it will be mlt minus 2. Simple mathematics, exponent rule, and we find out this. Why I haven't told you about f equal to ma? Because we have to understand this acceleration. We have to find its dimension. So first we will find dimension of acceleration. So acceleration as we know, it is change in velocity divided by time. Change in velocity. So let's find its unit first. Velocity, meter per second divided by time upon second. So again, exponent rule, ms minus 2. So this is the acceleration. Okay, moving on. And its dimension. So its dimension will be the dimension of velocity. So dimension of velocity minus 1 divided by t. So finally it is lt minus 2. Okay, and we can directly use it here. F equal to ma, SI unit will be mass, that is kg, acceleration meter per second square, and this whole bulky thing we can replace with Newton. So not only we are giving honor to Newton, but also we have replaced this bulky part. Okay, one more thing, its dimension, mass capital M, acceleration lt minus 2. So by whichever be the method, if you are going in a correct way, then you will find proper dimension. So we have used this formula, still the answer is same, because physical quantity, a particular physical quantity is a unique, has a unique dimension. It is a unique term. Okay, so now moving on. Work. Now this is going to be interesting. So work. We know its formula is W equal to Fs. Till class 9th we know this formula, but in class 11th, cos theta. You are going to study about this, why this cos theta stands here in the later sections. Okay, so work equal to force multiplied by displacement multiplied by cos theta, where theta is the angle between force and displacement. Okay, so remember one thing, cos theta is based upon hypotenuse. It is the ratio of two lengths, so it is dimensionless. Remember, all the trigonometric functions are dimensionless. Okay, so Fs, dimension of unit of force kg meter second square, and again multiplied by meter, so it will be kg meter square per second square. Okay, and also force, unit of force is also Newton, so it is Newton multiplied by meter, and again it is getting a bulky, so we will replace it by joule. So unit of work, SI unit, I'm talking about SI unit. I'm in this entire lecture I'll be using the terms in terms of using the units in terms of SI units only. So kg meter per second square, Newton meter, joule. All of these are SI unit representation of same unit, and but the terms are different. Actually, 1 joule is equal to 1 Newton meter is equal to 1 kg meter square per second square. Everything is same. Now moving on, its dimension of force m l t minus 2 meant L, and dimensionless, so it will be ml2 t minus 2. Okay, just leave it there. Let's talk about kinetic energy. All of us know that its formula is 1 by 2 mv square. So its SI unit of mass is kg, SI unit of velocity is meter per second square. So it will be kg meter square per second square, which is same as this. It means we can write it as Newton meter, we can write it as joule. Next, there is potential energy, but be very careful. There are several type of potential energies. What I am discussing here is gravitational potential energy. Gravitational potential energy with ground reference. Ground as reference. Again, why I have used this phrase here, we are going to understand it in upcoming chapters. But remember, in class 9th, you have studied this. Gravitational potential energy is mgh, but this is the half of the story. You will find another formula for potential energy also, but this is just if we take ground as a reference. Okay, ground or anything nearby the ground, if we consider that as a reference, then we use this formula mgh. So right now, don't get confused with this additional phrase I have introduced here, but this is for your future references, because in upcoming sections, when we are going to study about gravitation and gravitational potential energy in a different manner, then you will find a contradiction between this formula and that. So, but by the time, just follow this formula. Mgh, mass acceleration due to gravity. Now whichever be the type of acceleration, it is still acceleration, so we will use the same physical units and dimension for this g. Mass kg, g is meter per second square, and multiply by height means meter. So ultimately it is kg meter square per second square. About its dimension of m is m, g is lt minus 2, and h is l. So it is ml2 t minus 2. Okay, I just missed that part. We whenever we put this square bracket, this big bracket, it means we are dealing with its dimension. So if if I write dimension of work, so instead of writing this, I can put a square bracket. It means we are dealing with its dimension. So you can see dimension of gravitational potential energy or potential energy has same unit, same dimension as that of kinetic energy and that is same that of work, kinetic energy, potential energy, or any type of energy. They have SI unit joule, which is Newton meter, which is kg meter square per second square, and they have dimension ml2 t minus 2. So these all the quantities are correlated to each other. Some people can say that work and kinetic energy or work and potential energy have different nature. No, they are they have same nature because of work energy theorem, and work is totally associated with this potential energy also. So they are interrelated terms. They are all uh, the physical quantity of same nature. Okay, now moving on. So remember, any type of energy, if there is any type of energy, nuclear energy, electrical energy, heat energy, heat is also an energy, then you need not to think anything different, just to go through this unit and this dimension. But here there is another physical quantity which I'm going to introduce, is torque. Its symbol is tau, Greek alphabet again. So torque, simply a turning effect. Like if I hold this styler and I have one of the end and I apply force on other end, then instead of going in a straight line, it is rotating. That turning effect is called torque. And once again, you will be going to study about this torque in rotational motion chapter. So torque is equal to, its formula is some this is it looks like radius, but this is not a radius. It is just the distance between the point of application of force and the fixed distance, multiplied by f sine theta. Sine theta, it is the angle between this r, which later on we will call position vector, and force vector. So now if we want to find its unit, so it is meter into Newton, which we can say Newton meter, which is again kg meter square per second square, which is again joule. But it is not work. This torque is just the turning effect. It is not work. And its dimension is dimension of L, dimension of force, that is ml t minus 2. So finally it will be ml2 t minus 2. From here we can see that this torque has same unit and same dimension, that of work, but they are different quantities. They have different nature. So there is a long list, and there are over 200 formulae in your class 11th and 12th, and different terms would be there. So if you have a general idea of how to do this dimensional analysis, you can find dimension of any of the physical quantities. So for rest of the physical quantities, I am leaving it up to you. You can find their units and dimensions. But before I end this video, let's discuss about properties of dimension. Some of the properties I have included here. So dimension is independent of systems of unit. So dimension is basically uh, related to the uh, f- uh, fundamental quantities involved in that physical quantity. So it has nothing to do with the choice of uh, unit, system of unit. So if I'm measuring a length in SI unit or CGS unit or FPS unit or any other unit, still it is length. If I'm measuring mass in kgs or grams or in any other uh, unit, then still it is mass. So uh, so that is why dimension is independent of system of unit, because dimension is ultimately a representative of those fundamental quantities which are involved in that quantity. Next, uh, a unitless physical quantity must be dimensionless, but converse is not true. Remember this thing. What are unitless physical quantities? Like if I talk about refractive index. So refractive index is velocity of light in vacuum to velocity of light in a medium. And velocity is in numerator as well as in denominator. So their dimension will be cancelled out. So it is a dimensionless term. So this is what unitless also. So a unitless physical quantity must be dimensionless. If a physical quantity is unitless, if it has no unit, then it must be dimensionless also. But converse is not true. Now what happens, there are some fundamental there are some physical quantities which have units, though they are not SI units, but still they have unit, but they have no dimension. For an example, if we talk about angle, then angle have a supplementary unit which is called radian, but angle is dimensionless. Angle is arc upon radius, so both are lengths, both will be cancelled each other, so it is dimensionless. Other than that, if we talk about intensity, loudness of sound, so you probably know that the loudness of sound is measured uh, in the unit decibel, but that decibel has logarithmic uh, nature, and it is still not, it is again not an SI unit, it is just a ratio, and that represent the loudness of sound, and that loudness of sound is again dimensionless. It has unit decibel, but it has no unit, no dimension. It is dimensionless. Other than that, if we talk about amount of data, its unit is byte, in fact kilobyte, megabyte, but it is a dimensionless quantity. So uh, there are some other physical also, you can find it out of your own, which have unit but no dimension. Okay, if two physical quantities have different dimension, they cannot be added, but converse is not true. Okay, if two physical quantities have different dimension, they cannot be added. If two physical quantities have different dimension, one have dimension of length, other have dimension of mass, we can't add them together. Length cannot be added to mass, time cannot be added to temperature. So if they have different dimension, they cannot be added, but converse is not true. Means if they have same dimension, still they cannot be added. They can be added only if they have same nature, and even subtracted. so not only abstracted also. Okay, for a valid equation, dimension of each term of equation must be equal, and also the dimension of left hand must be equal to right hand side. This is called homogeneity principle of dimensions. So what happens here, for a valid equation, uh, let's I'm talking about this equation or any formula. Instead of formula we can use technical expression. So ut plus half at square. So you can see here, so this is a valid equation, and dimension of each term, its dimension, it is displacement, its dimension is L. Ut, U has dimension LT minus 1, T has dimension T, T will cancel each other, it will be L. And here acceleration, it has dimension LT minus 2, time square. So this is a valid equation. So each term must be equal. Yeah, dimension of each term must be equal. There are and also dimension of left hand side must be equal to right hand side. So obviously if they have same dimension, then that will be true also. So last thing, pure numbers, trigonometric function, logarithmic, exponent, etc. are dimensionless. So later on you will find such problems based upon these properties, and we will be going to study about what are the uses of dimensional analysis. So see you in the next video.